Hello everyone and welcome back to this video. So in this video, as you have seen in the title, we will be covering so this is going to be the first video of the many videos that I'm going to make on computational neuroscience, right? So in this video, we are going to focus on brain computer interface. So how we can develop brain computer interfaces, right? So and what is the logic between them? How do they function? So we are going to learn all that in this video. So thank you for clicking on this video and let's get started. I'll share the video. Right. Right. So let's get started. Uh, Introduction to computational neuroscience and brain computer interfaces. So I'm going to provide you with an overview of the field, and we're also going to learn. So mainly, we're going to learn how these brain computer interfaces function and how can we extract the signals that are propagated in the brain, and then how we can make sense of them, right? How can we uh, learn patterns in those signals, and how we can use those signals for understanding the human brain, understanding human psychology in general, right? So what is computational neuroscience, right? So basically, the brain is a computational machine. So it has been proved. I mean, of course, there is a debate on it, whether brain is completely computational, or there is some more. Some people argue that there is much more to human psychology than mere computation, than many engineers assume, right? So again, leaving all that behind, mainly, at least on a very high level, brain is a computational machine, right? So basically, we have electrical signals, right, propagating or traveling through neurons, right? So why and so which is fundamentally computational. So so if you can try to model these signals and try to uh, understand them, or model the signals in the brain using mathematical models, right? And then so try to understand brain, or analyze the brain. So that is the field of computational neuroscience, or so where we computationally model the signals in the brain and try to understand them, try to recognize patterns in those signals. So that is computational neuroscience. uh, and in this video, specifically, we are going to delve into brain computer interface again. So I'm going to make many videos in the field, in the field of computational neuroscience. So this video is just high level overview in the field in brain computer interfaces, right? So brain computer interface enables communication between the brain and external devices, allowing control through thoughts, right? So we also have an application. This is not just a hypothetical field of research. So we are not just doing research. We are not just trying to understand the human brain, but there is an actual application, right? So there are many people with disabilities, right? So which makes them hard uh, to interact in the real world. So for them, we can basically uh, model or try to understand the signals of the brain, and maybe let them control some external devices, right? Just like giving them like an extra limb, right? So maybe just providing with an artificial limb, right? Providing them with an artificial limb. So yeah, it has an application. And then yeah, people with disabilities can actually use it. And there are many other applications, and there are also many uh, futuristic ideas too that we can do with BCI, brain computer interfaces. Elon Musk, right? I'm pretty sure that a lot of you people will know that Elon Musk has been working on this chip called Neuralink, right? I think they've also like released a specific version of it. They made a video too, like the Neuralink team, right? So where you can actually play a game, right? Just with the control of mind. I mean, these things, right? These research, they don't have direct application as of now, but they are just fascinating to even think about, right? So it's just fascinating, the amount of let's say, the amount of control we can have on human brain, and the possible applications, right, that we can build in the future. So they might not have specific applications now. As of now, they might not be of direct use, but they will be of so much use, right? They'll have so much potential in the future. These type of fields, right? So anyway, moving on. So monitoring brain activity. So the first step, to understand the human brain, before even understanding, well, how can we capture the brain signals, right? How can we even more or even get them, right? How can we get them so that we can learn some patterns out of them? How can we get them? How can we even extract them from the human brain? Again, a brain is a electrical machine, right? We can think of brain as a machine, right? It interacts with electrical signals, right? Which we are already good at, which we are already good at, processing and all them. We have already devised techniques to process electrical signals, store electrical signals, and even find some patterns in them, right? We already have some expertise. We humans have already developed methods, with dealing with electrical signals. So how can we get them, right? So there are like three main techniques. Again, I'm sure there are many, and I'll probably make a video on this, specifically on monitoring brain activity. I'll probably make a video on it in the future. So there are three main techniques for monitoring brain activity. So one, there is electroencephalography, right? Then we have magnetoencephalography, and we also have functional magnetic resonance imaging. So what is electroencephalography? So in electroencephalography, we'll have our 1 second. Right. Sorry for that disturbance. Anyway, so in electroencephalography, what we'll basically do is we'll basically put some uh, electrodes in the scalp, right? And due to the interaction of the electrons, due to the electrical signals exchange between the electrons, we can basically uh, so some radiation or some electrical signals can actually be uh, detected in the scalp actually. So that is electroencephalography. We'll get the electrical signals. And we have magnetoencephalography, which is we'll place some sensors in the brain, and the magnetic field that is being generated due to the transfer of these electrical signals will be recorded, right? So that is and we can actually plot those signals, and from that we can understand the activity of the brain. So that is magnetoencephalography, that type of monitoring. And we also have functional magnetic resonance imaging, which basically works on this principle, right? So again, this is for like computational neuroscience, understanding the human brain. So so yeah, understanding the human brain. These are techniques to monitor brain activity for understanding human brain, not specifically for BCI. So in functional magnetic resonance imaging, it works on this biological principle. So the most active part of the brain, so the part of the brain that is the most active, will basically need more oxygenated blood. So because of that, more oxygenated blood will flow towards the part that is most active uh, for a process, right? So, and based on this principle, we can actually, uh, by tracking the changes in the blood flow, we can actually uh, understand brain activity, or understand brain activity, and monitor brain activity to some extent, right? So that is functional magnetic resonance imaging. I think for the most part, for many projects that I have looked at, EEG is the most common, electroencephalography, maybe because it is the most cheapest, and then also it is most relevant for BCI, for like um, it's a classifying human thoughts, right? So for that part, electroencephalography is probably the most relevant, and it's also cheapest compared to cheaper to extract compared to magnetoencephalography. So EEG is the most common. Electroencephalography is the most common. Anyway, so these are the three monitoring techniques. I'll also try to make a deeper video where we go into the depths of these techniques in the future. In the future, I'll make a deeper video. Anyway, moving on. So how can we model signals? So once we have the signals, right, some form of signals, I'll say from these three, from any of these three techniques. So how can we model these signals? How can we understand these signals? And for understanding the brain, right, for finding some patterns in these signals to understand the human brain, right? How can we do that? Well, if we look at it, if we look at the signals, they may appear to be absolutely random, right? So the patterns are very, very uh, intricate, and they are very trivial. They're almost like we can't actually see the differences, right? We can't find the many patterns because they are like hidden in some sense. So we need some computational machine, right? We need the computer to basically try to understand these patterns. So so how can we do that? How can we model these signals? How can we try to understand the patterns, the different patterns in the signals, right? So how can I do that? Well, that is where deep learning comes in, right? So welcome to this channel, right? We teach deep learning here. So this is where deep learning comes in, right? Well, how does it work? So I'll try to provide you with a basic overview of neural networks, a very very basic one. If you want a deeper understanding of deep learning, uh, check out this channel. This channel, Learn AI with Joel Banyan. You can go through the videos. I have many videos here. So anyway, so how does a perceptron work, right? So this is called a perceptron. So before we try to understand how can we model a signal, let's look at how can we model, let's say anything, right? Let's say we have four variables and one output, right? How can we model the relation between four variables, any four variables, or even three variables, and an output, right? So for example, let me give you a classical example to make you understand this. So let's say you work in a real estate company, right? And your job is to actually predict the price of a house depending on some factors. And for example, those factors can be the height of the house, those factors can be the distance from that house to, let's say, the nearest school or the nearest market. And there can also be other factors such as the place in which the house is located. That also determines the, let's say, the price of the house. And then you can have multiple variables like that, right? So how can you model the relation between the variables and the price of the house? So how does these variables affect the price of the house, and in and how do they affect the price of the house, positively or negatively, right? So you can model, your job is to model these variables to the price of the house. How can you do that? So the solution to it, the one way you can look at it, is to actually build an idea of a perceptron, right? So first of all, you can model a linear equation. You can create a linear equation, a straight up linear equation, which is basically and you can build a linear equation are these factors, and the output is the price of a house. And you can associate each factor, let's say each value x. So we consider x as the input factors. We have x1, x2 up to xn, all the n factors we have. So you can associate it, or you can multiply each factor, each value, whatever that be, whatever numerical value that might be. You can multiply that factor the with the weight, right, with a random number. And then you can also we'll also add a random weight here, which is called bias, right? So these w's are called weights, and this is also called the bias. And what you can do is you can collect many records of many houses, right? Many houses that have been already built, right? So there may be many houses that have been already built, right? So you can collect the prices of the houses and the different values corresponding to the different variables that you have considered, or different factors that you have considered. You can get the corresponding values for different houses and also get the corresponding prices. And what you can do is to actually build this linear equation, right, and update these weights. So you have these weights, right? You have w's and b, right? So update the many w's that we have, and each w is different, right? So you have if you'll have a specific w, a specific weight value for a specific factor, and you'll multiply these weights and also the bias. Okay, you'll multiply the weights and add the bias, and you'll update these weights. You'll update the w's and b such that uh, for each record, you'll have many records, right? For each record, the output value of the model that you have created is as close as possible to all the records, right? So it should be closer to the 1, 2, 3, and 4 and 5, right? So that is one good way of thinking about it. And how will you update the weights? Well, what you'll do is you get the error. Error is nothing but the difference between. So in each step, you'll calculate the error between the predicted price and the corresponding price, and you'll do that for all the records, right? Many houses. All right, you will subtract the predicted house with the actual house, and you'll do that for all the records. You'll add all the errors, and you will update this weight such that this error is reduced, right? So what you'll do is you'll find the derivative of the weight of each corresponding weight, each weight, and then each weight corresponding to or let's say with respect to the total loss function, right? The total loss function, right? So that's how you do it, and you will update this error for multiple times, and hopefully, and at last, and almost definitely, if you do it for long enough, you will create a model, or let's say here there's a linear equation with the right values, with the right values for the variables, which can predict the price of the house with the with the given this, given the values for the input factors. So basically, I've modeled the relation between the factors affecting the price of the house and actually the price of the house. So that is how you can model anything, right? So that's how a perceptron works. So that's what one neuron in a neural network does. And in a neural network, right, what you basically have is you have many neurons that perform the same calculation. So we have many weights. So each neuron has some input. So this is the input layer. So these are not actually computational neurons. So they don't have any calculation. So they're just input values, input factors, and each factor value input into a neuron, and each neuron has different weights. And so one good way of thinking about is like, of remembering this, let's say, is to actually think that each connection or each line you see here has a specific weight value, right? So what you do is you have many neurons. So each neuron has its own weights, and each input has its own weights, a weight, its own corresponding weight, right? Which will be updated during the gradient descent time. So the updation of this parameters is actually called as gradient descent in neural networks. So, and you have you will have the output, which can be anything, right? We can have any number of neurons, any number of outputs, right? So maybe you are printing like 4 values in the output, right? So anyway, so you'll have like many values in the output, uh, and these values will be predicted, right? And so the predicted values, you'll calculate the loss function, which is actually the difference between the predicted value and the actual value, which you have collected, which you have recorded, right? Which you are trying to model, right? Uh, and then you'll update these weights in order to decrease the loss function. And you might have predicted that the more neurons, and the more the connections, the more the complexity of the network, the more powerful the network is. Right. So the more harder relations you can model, right? So that's how neural network works. And why are we necessarily talking about predicting an output, right? So this is just like taking an input and predicting output, right? So because one good way of modeling things is to actually uh, classify them, right? So if you can think about it, so let's say we have multiple signals. So one good way of understanding these signals, understanding the patterns in these signals, is actually to classify these signals, right? So let's say you want to understand, uh, let's say you want to understand the patterns in a signal. So what you can basically do is to actually uh, monitor or extract the signals, right? You can extract the signals in different activities. So while the subject is, let's say, doing different activities, or yeah, performing different activities, you can monitor the signal, right? Extract the brain signal, extract the EEG, and you can in the same framework, you can have the signals and the corresponding activity, and you can model the relation, right? You can model the relation between the signal and the activity. And what you have basically gained after training is a model, is yeah, a model that understands the patterns in the signal that corresponds to the different activities, right? The different features of the signals. So what you can do is to get the signal and make a model, make a neural network that can actually that is actually required to predict the features of the signal. And on doing that, after training, what you've basically done is you have created a model that understands the patterns in those signals, right? That is good with the signals. So that's what we're doing, right? I hope you understood what I've said. Uh, so the next thing is that, well, you might say, uh, right? So what you might assume the next step is is to just take the signal values, right? We have certain signal values. So as time progresses, we'll have certain values, right? So you'll take a very small time gap. Is that what you say? Okay. So within small time intervals, you'll get the corresponding, let's say, x value. So whatever that is. So and then you might say you'll put in the corresponding x values in the input layer, and in the output you'll have one neuron predicting the activity the subject might be doing, right? So let's say the subject is laughing, right? So there may be some corresponding signals, right? Or let's say the subject is trying to move his hand. So while the subject is moving his hand, there might be some corresponding brain signals, right? EEG signals, right? So you can get these signals and make the model. So given these signals, you can make the model predict that the subject is moving his hand. And well, and for many activities, you will get the signals, right? So for while the subject is doing many activities, you'll get the signals and try to model the relation between these signals and the corresponding activity that the subject is actually doing. Well, there is a problem with this, with actually using this neural network. There's a problem with that with actually using the neural network, this general neural network. Well, the problem is that the sequential nature of signals will not be uh, easily or efficiently or effectively uh, learned, right, or tracked by neural networks, right? So if you directly use a simple neural network like this, right, the neural network will not be able to efficiently and effectively capture the relation, uh, the sequential nature of the signal, right? So because so that is why when we are dealing with signals, dealing with signals, it is better to come up or use an alternative type of neural network, which is called recurrent neural networks, right? So we have another type of neural networks which are called recurrent neural networks, which are specifically developed for dealing uh, with with time varying data, right? So we have many time varying data or sequential data, such as signals, and also language. So if you think about language is also sequential, right? So the word that I have just said before very much affects the word that I'm going to say, right? The previous word very much affect the word that I'm going to say, and there is a sequential priority or sequential importance, right? So the word I have just said will have greater influence on the word that I'm going to say, and so any sequential data or data that is time related, or yeah, sequential data, you can say time sequential data, uh, any data like that, when you're trying to model that type of data, right? Like again, how do you model that type of data? Well, you take the data and you make the model predict certain feature of the data, and while doing that, in that process, you can basically learn the patterns in that sequential data, right? Again, uh, so so how does an RNN work? So this the neural network that are used to model sequential data are actually called recurrent neural networks, right? So how do these RNNs work? So this is how RNNs work in general. So you can think of these H blocks as perceptrons, or they could actually even be neural networks. They can have multiple neurons actually. But anyway, so what you have is you have a sequence. You have a sequence of inputs x to let's say t plus one outputs, t plus one values. Right, you have a signal, right? You have signal. In a signal, you have many values that are sequential, right? Many x values, let's say, with respect to time. With respect to the x-axis, which is time, you have many y values, right, in a signal, right? So what you do is you put you put the y value, or let's say you put the input value, which is x, right? You put the input value at each time step, right? So we have multiple values, x values, right? From x to xt plus 1, we have many x values, right? So you put all these signal values inside the neural network. And again, so basically, all these ht minus 1, ht plus 1, well, the boxes are all the same, the weights are all the same, so you have the same neural network, right? but but it predicts different values because the input changes, right? So the neural network and the weights are all the same, right? The neural network and the weights are all the same, but basically we have unfolded it. As you can see in the first diagram, this is how the actual diagram is. So this is the actual diagram, right? So you have x, and you predict the output, and there is sometimes uh, some kind of transfer of hidden information, or transfer of knowledge, right? You can say from the previous time step to the next time step. So once you unfold this diagram, we'll get this diagram. So basically what I'm saying is, you have the same neural network with the same weights, but rolled out, right? But with different inputs, right? With different sequential inputs. So what you have is, so first of all, you put in x value, you put in an x value, and again, it is your wish if you want to predict an output. It depends on the problem. So if you have a many to many problem, so a many in a many to many problem, the input is a sequence and the output is also a sequence. So for example, in problems like let's say translation, you have many inputs and many outputs. So then you might have to predict an output at each time step, right? However, in our problem, we don't need that. We can neglect these both circles, ot minus 1 and ot. So anyway, so you'll put in this xt minus 1 value, and you'll calculate a hidden value, or hidden knowledge value, or hidden variable, or hidden weight, or hidden value, which is ht minus 1, which is going to be transferred to the next time step with the output xt, right? So this ht minus 1 will also be considered while during the calculation of ht, and this ht value will be uh, considered while calculating ht plus 1 with input xt plus 1, and you can predict the final output, which is ot minus 1, ot plus 1. So you have a sequence and one output again. So we have three values which produces one output value, and these output values are in a sequence. So what basically happens is, during the calculation of this ot plus 1, ht plus 1 plays a role in the calculation of ot plus 1. ht plus 1 influences ot plus 1, and in turn ht uh, uh, influences ht plus 1, and also ht minus 1 influences ht, which in turn influences ht plus 1. So the calculation of this value depends on all the input values, all the input signals, and also the hidden values, ht minus 1 and ht, right? So uh, that is how RNNs work. That is how recurrent neural networks work. So basically, you can visualize this as the flow of information, right? You can visualize this as, each value in the signal plays an important role in the final determination of the output, right? So that is how you can think of it. And what you also have in these sequential neural networks is some kind of gates, right? You will have some kind of gates which determine the amount of influence the previous uh, the previous hidden value or hidden state should carry or should have on the input of the present output. Again, all of these values, all of the weight values, again, we are going to have weight values, right? We are going to have weight values, and all of the weight values, right, are going to be updated in order to minimize the loss between this ot plus 1 that we have predicted and the actual ot and the actual output that there is, right? So that's also one thing to remember. And let's go to next slide. So what is happening? So what is happening in this little box, right? So in this little box, so what we basically have here is you have the previous hidden state. For if you are so for example, now we are calculating ht, so the hidden state at time t. So you have the previous hidden state, the value, the previous hidden state, and you have a specific weight. Again, these weights are common for all the time steps, right? So for all the time steps, these weights are common. Uh, so you have the previous hidden state. So you multiply this weight with the previous hidden state. We add the bias, and what you also have is you have the input, right? So you also multiply the input with another weight u. So what weights do we have now? We have w, u, and b. These are all weights which are going to be updated to minimize the loss function, which is going to be the output, right? Output at the last step. And what we are going to do now is take this AT, and we're going to put this AT in a tan h function. So we have this is a tan h function. And this tan h function, so the output of a tan h function is going to be in the range of -1 and 1. So this is called an activation function. So in every almost many neural networks will have, so in each neuron, we can actually apply an activation function. They have their specific uses. I'll not go into that in this video. Uh, so you have an activation function, tan h, which uh, so in a tan h function, you can input any value, and the output is going to be in the range in the range of -1 and 1, right? So that's what tan h function does. So based on this value, we are going to convert it into either 0, -1 and or any number between the range of -1 and 1, right? And the output, the output OT is equal to C plus V into H of T. So what are we doing here, right? So we have C, which is okay. So we have C, which is which is going to be a weight, right? Just like B, W, and U, we have C, which is also going to be a weight, and then we're going to add that with V. V is also going to be a weight, and we are going to multiply that by H of T. And since V is going to be in the range of -1 and 1, so if uh, so we have a chance of completely neglecting the hidden state of that particular time step. So the tan h value can very well be 0, very well be equal to 0. So if it reaches 0, we can actually we are going to completely neglect the hidden state of that specific time step. We also have that opportunity, just saying. And then if you want, you can predict the output of that time step, right? Again, we don't have to predict the output. All we are considering in this sequential model, in the sequential neural network, is actually the calculus of the hidden state, right? Which is based on input value and also the previous hidden state. So that is very important. And also, just like this, with the same architecture, we have different kinds of uh, architectures, right? We have different kind of networks too. So this is called a GRU, a gated recurrent unit. So these equations correspond to GRU, gated recurrent units. And here we have LSTMs, which are called long short term memory. These are very famous ones. So in the GRU, what we have is we have more gates, right? So these gates determine so these are like gates, that determine how important the the previous hidden state is, and how important the current input is, right? So these determine, you have gates, we have more gates that determine the importance of the previous hidden state and the current input, right? So here we have first of all, we have R gate, right? Which is going to be sigmoid function. So this is called a sigmoid activation function. And just like tan h, so this sigmoid activation function is going to be, it can uh okay, like sorry for that disturbance. So my the charging ran out in my computer. Anyway, so in the GRU we have two gates, right? So these gates are basically outputs of a sigmoid function. So we have a sigmoid function. This is called a sigmoid activation function. So, so output of a sigmoid activation function, similar to tan h, is going to be in the range of 0 and 1, right? So in tan h we have -1 to 1. So here we zero, here we have 0 to 1. And so this R gate we have is going to control the influence the previous gate, ht minus 1, is going to have on the output of, or on the hidden state of the current gate, current hidden state, right? So the influence of the previous hidden state on the current hidden state is determined by this gate. So if it is more closer to 1, then, well, there is going to be more influence of the previous hidden state on the current hidden state, right? And then this CET, okay, so we have this UT, right? So this U gate, well, that is going to determine the, again, it's going to determine the influence of the current, so it's going to determine the balance between the current hidden state, the influence of the current hidden state and the previous hidden state on the current hidden state. So again, these are all, so the gate is also going to influence, is going to be influenced by these weights, right? So these weights are, again, are going to be updated. So what we are basically doing is actually regulate the influence of the weights, the previous hidden states on the future hidden states. So basically, this balance is going to be decided too. So this balance of two is also going. This balance also is going to be decided, right, in the gradient descent process, in the Bragg propagation process, right? So if here in LSTMs we are just going to have more gates, right? We are going to have many gates, uh, and this. Yeah, so we have F gate, which is going to be determine the influence of the uh, influence of the previous hidden state value, and then we have I gate. Again, right, just many gates, right? So if you have many gates, we are just going to increase the complexity, and uh, this uh, this question of which hidden state should we prioritize, right? uh, Again, we're just going to add multiple complexity, more complexity to it, hoping to solve this problem, hoping to finally answer the question of what is important, what in the sequence is actually important. So this is LSTM, right? These are recurrent networks, right, which run by time. Again, there's one more architecture which is probably uh, which is, I'm sure all of you are aware of it. I mean, at least in practice, even if you are not aware of theory, it is transformers, right? The transformers architecture, right? So I'm sure you are aware of GPT, which is called, which is basically generative pre-trained transformer. So this is a transformer architecture. Again, it also deals with time series data, but it is different from RNNs, right? So I'll just show you in a very, so I'll just show you in a very brief. I'll just give you a very brief outline of what transformer is doing. So here, this is not like the RNN, LSTMs, and GRUs that we have seen before. So we don't have recurrent time steps. We don't have separate time steps. But here we have, here we can just input the complete embedding at the same time, or a complete signal at the same time, and we'll get the output probabilities. How do you do that? So so have the we input embedding. So we'll put in the input embedding, and it goes through certain process. It goes to attention process, which I'll share in just a minute. And then we'll have a feed forward neural network, which is our normal neural network, right? And we have and the output is going to go into another multi-head attention, which again we have output embedding, which is going to be updated as in the training phase. We're going to update this output embedding. This value is 2 as you go on. And okay, so this is going to be okay. And then finally, after a few feed power neural network layers and some linear layers, we're going to get the output probabilities, which are, we're going to get the output probability, the next time step value, right? And if we are doing many to many application, if we are working in a many to many application, we'll in turn put this output probability into this block right here, and right, uh, until we finish the output sequence, right? So here we don't need, we do not need multiple output embeddings. So we can just do this in one step. We have multiple inputs and just one output. We don't need to plug this output probability again. So plug this output probability again into this block. So we don't have to do that, because we are in a many to one application, right? We are taking in a signal and predicting the activity, right? We are doing classification on in the very, right? We are just doing classification, right? So we are just doing classification, right? We don't have to plug in the output of the transformer again. So we have to do that in many to many case scenario where the output is also a sequence, right? So you can see this in language, right? So when you're many tasks that deal with language, you can see the task is actually going to be many to many task, many to many application. So then you will have to uh, the output of the model is going to be the input of it again to predict the next sequence, right? Again, not go into that. So so the main step here in the transformer is this attention phase. So you see this orange block, right? Multi-head attention. I'll ask you to neglect these add and norm layers as for now. So if you want to go into them again, I'll put in the relevant links of the videos in the description. So the relevant videos I'll try to put in the description if you are interested to learn more about them. So what is happening in this multi-head attention phase? I'll try to cover very briefly just to give you an idea of what is happening. That is what that's what's important. So for example, if you have two input values, two sequence values, with in some time period. So let's say, uh, generally when we deal with transformers, we are dealing with language. So we have here in this example, words are given, thinking machines, let's say. So these so yeah, let's say you have some two values, right? Two sequence values, x1 and x2. So what you'll basically do is you will generate some weight matrices, which are again going to be updated in the back propagation phase, in the gradient descent phase. I don't need to worry about where they come from. Initially, they're going to be random again. Soon they'll in the training phase they're going to be updated in the gradient descent phase, in order to again to reduce the loss function. But okay, so we're going to have weights which are going to be WQ, WK, and WV. So what we're basically going to do is we are going to multiply this x1, x2 with some weight matrices, right? So we're going to have three weight matrices, right? And we're going to multiply these weight matrices with with each embedding, and we're going to get three outputs, which are going to be q1, q2, k1, k2, v1, v2 for two uh, inputs. Let's say two time stamps or two time states, right? Two time points, let's say. Then so we have three, right? We have three vectors for each input. So these three vectors that we have generated are called query vector, key vector, and value vector respectively, right? So we have query vector, key vector, and value vector. So what we are going to do with this query, key, and value vectors, right? So after we calculate the query, key, value vector, we are going to find the similarity, right? We are going to find the similarity between each query vector to uh, other key vectors, right? So we're going to have many x values, many values in the sequence. So each query vector of one sequence, let's say, or one time point, we're going to multiply that or get the dot product. In the, if we speak of the correct mathematical terms, so we're going to get the dot product of the query vector of each time point, or each value of at a specific time point with the key vectors of all the other key vectors of other time points or other values, other x values, right? Other key vectors of the other x values, right? So what we are basically doing is we are going to find the attention scores or find the similarity, right? So we are going to find the similarity uh, between the query and key vectors. So so uh, if the if the query and key vectors are more similar to each other, then the dot product is going to be higher, right? So if the dot product is going to be higher, well then more attention will be given, or more relation between will be given to those specific two points, right? So these weights also should be updated such that, so if two words are, if let's say if two words, right, let's take words. So if two words are similar, then what will basically happen, what the model should do is to update the query and key vectors such that the dot product is higher, as high as possible, right, for those two similar words. And in order to do that, it has to update the weights, right? So it has to make the dot product as high as possible, because let's say these two words appear frequently, right? So these two words appear, let's say, next to each other, then the dot product should be higher, right, because they are both related strongly, right? So this relation is calculated by these transformers, right? So in the attention mechanism, we are calculating the relation, right? So the relation between uh, points, or relation between each point in the time in a sequence, we are going to calculate in this attention, in this attention mechanism. And based on that we are going to perform our calculations, right? And based on that we are going to do our calculations. That's how we calculate attention in a transformer. And 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 this mechanism works wonderfully for language, and might also work for signals, other type of signals too, right? And even with basic BCI, we could incorporate transformers, right? Anyway, so we have I have two more slides here. If you wish, you can take a screenshot and read if you are interested. Again, I'll not force you. So decoding of thoughts, again, as I've told you, we can also use in lie detection or criminology. You can also use it in memory extension. Very interesting, right? You can also store human memory. That's what I mean. Okay, would be very interesting thing. Again, I'll try to make more videos on this topic. Uh, More and more will be coming on human psychology in general, right? uh, I'm getting quite interested in this field. I'll make more videos on human psychology too, right? We also have telepathy communication, right? Brain to brain interface. Okay, that's okay, interesting. And automation and control, we all know that. And also future applications, we have intelligence sharing, a very futuristic idea, where we can actually, I think, share intelligence between brain, or I think just, I mean, we're just talking about transformation of information. I don't know. And then brain energy harvesting, right, to actually use the energy from the brain to power low energy devices. Very, I mean, like, very futuristic, right? I mean, these are all very interesting applications, right? So I mean, they might not necessarily be useful applications, but why not, right? I mean, they will open up doors, right? So once we get to the key, uh, we can open multiple doors which we are not even aware of, right? So then localized BCI, which is enhanced signal processing by localizing electrode placement. Okay, I think this is a problem that we have to solve. Okay, anyway, so this is about BCI. I'll try to come up with more videos on this topic, especially computational neuroscience in general. We'll learn more about it. We will try to understand more of it. I'll definitely come up with more videos. So thank you for watching if you have. And if you have any advices for me or any queries in general, please do message me on LinkedIn. I'll be available. And thank you for watching. And I'll see you in the next video. I'll take care. Thank you.